Today is May 10th, 2007. We're doing an oral history interview for the archives at the University of Alabama in Huntsville. I'm Charles Lundquist. Our interviewee today is Sam Zeman. Thank you for coming, Sam. It's good to have you.
Thank you, Charles. I appreciate the opportunity to be here.
We'd like to start out by letting you tell a little bit about where you spent your youth, where you were educated, and how you got into the space program. Can you do that, please?
Yes, I'd like to give a kind of a quick overview, if that's okay.
Sure.
I've been in Huntsville since January of 1951, over 56 years, and I think it's a wonderful place to live. The Army brought me here, and I've been involved in rocket and missile work for about 52 years. I dropped out for a few years, but I'm back into it. I'm working again through my old employer, the Stone Engineering Division of ASI. I was married almost 56 years. I lost my wife late last year, but we raised two children, a son and a daughter. My son is Mark, a doctor, dentist in Cumming, Georgia. My daughter lives in Huntsville. She works for a financial company. And we've just enjoyed being in Huntsville. After I got out of the Army, I worked as a civilian employee of the Army for 5.5 years, and then I went to work for the Thiokol Corporation for 31 years. And after that, I retired from Thiokol, and I didn't stay retired very long. I started consulting, and I did that for over 12 years, and I'm still at it. But I need to go back and tell you where I started from.
If you would, please.
I was born in Chicago in 1928. I'm giving away my age here. And I attended the public schools there. After graduation from the Harrison High School, I attended the University of Illinois in Champaign-Urbana, took general engineering for 2 years, and then changed to the chemistry curriculum for the next 2 years. And I graduated with a BS degree in February of 1949. My minors were in math and physics, but even before I went to college, I was an eager student, and I went to night school while I was going to high school, and I was studying refrigeration, air conditioning, radio repair, and chemistry of explosives. After I graduated from college, I worked as a chemical analyst in a laboratory for a short time, but the work seemed very boring, and I didn't like it, so I quit and went into the commercial refrigeration business. I was selling and installing and servicing commercial equipment for grocery stores, meat markets, and so forth. I had a good start of a going business until Uncle Sam came along and asked me to report for military duty.
What year was that?
That was in November 1950 as a result of the Korean War. I was paid $75 a month to start as a private, and I went to Fort Leonard Wood, Missouri for basic training. After 8 weeks of training and some interviews, I was sent to Fort Myer, Virginia, outside of Washington, for more interviews and assignment. And there the Army assigned me to one of their high priority installations where they had hard to fill scientific positions they wanted to staff. Although I didn't know it at the time, I was very fortunate to be sent to Redstone Arsenal. And that's
So when did you arrive here in Huntsville?
I arrived in Huntsville on a Sunday in January of 1951.
That was very shortly after von Braun and his team
That's
got
true.
here then. They
That's
got here
true.
in 1950.
Well, I found out that you reported that Dr. von Braun went to the Army people and requested that they select some technically qualified people from their ranks to staff their open positions. And the Army group that provided that technical talent at Redstone was the 9330th Technical Service Unit. And that's what I belong to, and that's what you belong to also.
Now, there have been several interviewees who have. Nobody has talked very much about just how that unit operated, and maybe this is a good time to get some of that in the record. If you could do that, please.
Well, we got up early in the morning, and had our breakfast, and then there was a call for formation out on the road next to the barracks. We lined up, and the first sergeant came out and checked to see if everyone was there that belonged there, and he made some announcements. And if it was after a weekend, he complained about those who had gone out and did things they weren't supposed to. But after those announcements, we generally went to work. And we got into trucks and whatever transportation was provided by the Army, and we went to our work areas. In my case, I worked across the arsenal at the south end of Redstone Arsenal in Building 7120, which is also the Rocket Auditorium, across the street from the headquarters building at that time.
What organization were you assigned to then?
I was in the Ordnance Missile Laboratories in the Propulsion Laboratory, which is now called the Propulsion and Structures Directorate.
Who was the director of that lab at the time?
I think there was a colonel, Joe Rush was in charge of the lab at that time. Was the overall director, and Frank James was our leader.
Okay.
At that time of the year 1951, Huntsville was a sleepy little town of about 16,000 people, and it seemed that everybody came to town on Saturday morning and gathered around the courthouse and the streets surrounding the square, and there were usually some fiddlers and pickers and plenty of storytelling going on.
And Cotton Row across
Cotton Row, exactly.
across the street from the courthouse.
Exactly. I'm glad you mentioned that. The bales of cotton were out there on display, and I didn't watch what they did with them, but they were always there, and there was transactions going on. The work that I was assigned to in the propulsion lab, it started out, well, first with some indoctrination and literature studies, and then I was assigned to work on rocket propellant fuels with primarily high energy fuels at that time.
Liquid fuels or solids?
Solid fuels. I'm
Solid.
glad you mentioned that, because most of our Army folks were in the liquid fuel area supporting the von Braun team, and a few of us were sent off to support the solid propellant area, and that's how I wound up in that area, which became a career for me eventually. The fuels that I worked on at that time were based on boron and the borohydride derivatives, and together with a civil service chemist that I worked with, we also set up a facility to make cast double base propellant. Now, double base propellant was the only type, or the type that was in service in military rockets at that time.
Describe what a double base is.
A double base is a propellant that has two main ingredients that are independent explosives themselves, or combustible materials. In this case, it was nitroglycerin and nitrocellulose. And the
Fun stuff to work with.
fun stuff, yes. And after several months in the Army, in April, in fact, in 1951, an Army chaplain married me to Nora, my high school sweetheart, on post here at Redstone, in the troop area, in the small chapel next to the barracks almost. And
By the ball field, too, I think.
Yes. We were the first couple from the 9330th Technical Service Unit to get married on post, and so I missed some of the fun, in quotation marks, of the barracks life. After a couple of years in the Army of working in the laboratory and going to meetings, well, after I got married, of course, I was able to move downtown, and I just reported at least once a week to the troop area for lessons in various things that they provided. The rest of the time I was on my own, so it was a very good life because the military requirements were minimal, and most of the work was technical.
So what did you do then after you were discharged from the Army?
Well, after my 2-year duty was completed, I became a civilian employee of the Army. I worked for 5.5 more years. I worked in the same laboratory and basically started out doing the same work at about 6.5 times the pay that I had received as a
That was
military.
pleasant.
That was pleasant, I agree. But I was still eager and took some courses at night at the University of Alabama Extension Service at Butler High School. And it may be of interest to say that I took a course in German, which was taught by Magnus von Braun,
Really?
brother of Werner von Braun. And he did an excellent job of teaching. And at first, well, my first day or two at the class, I didn't know who he was. And during break time, we were standing outside the building, and I spoke to him and told him I was surprised he didn't have a southern accent. And he told me he was not from the southern part of Germany. And I was surprised that he was from Germany at all, because I thought he was an American-born person.
So his English was very good then?
His English was excellent. I also took later a course in chemistry that was taught by Dr. Karl Hager, one of the German scientists, and he did a great job. Not only did he give us some good chemistry lessons, but occasionally he got off the subject onto side issues, and those were really interesting. At the propulsion lab, I was put in charge of the inorganic chemistry group, and my supervisor, Dr. Carol Bjork, asked me to concentrate on igniters and ignition, because he thought there was a big need for improvement in that area, so I did that. And he also said he wanted to make a tour of facilities that were involved in rocket fuel research, and he invited me to go with him. And that was a real great experience.
What places did you visit?
Well, we went to the Allegheny Ballistics Lab, usually called ABL, in Cumberland, Maryland. We went to the Bureau of Mines in Pittsburgh, Picatinny Arsenal in New Jersey, the Naval Ordnance Lab in Silver Springs, Jet Propulsion Lab in Pasadena, Aerojet in Azusa. They were in Azusa then, California. And we went to the Naval Ordnance Test Station at China Lake, California.
That's quite an education in itself, visiting all those places.
Absolutely. Absolutely, Charles. It when I finished that series of trips, I practically had enough, a wealth of knowledge to get another degree. And it helped me kick off my new assignment over the next few years, where I worked on rocket ignition and developed metal oxidant igniters. And so many of the things that we did were intended to improve safety or performance of these items. And we were very successful in some of the things we did. They became classical and are still practiced today, some of the very basic things that we did.
It's a good thing to realize that you made that contribution.
Well, I'm very proud of some of those contributions we made in making things safer, because when you talk about rockets, one of the first things you want to do is make sure that the people handling them are not injured in any way by handling the devices that you have come up with.
Where did your career go after that time then?
Well, we worked on components, we did some basic research, but then after the 5.5 years, I branched off and decided to go to work at Thiokol. Before I went to Thiokol, though, I did quite a bit of work in the high-altitude ignition, where I thought there was based on some early experiments, that there was a potential problem, and it turned out...
I think it was a problem. People
It was a
worried about it
problem.
a lot.
It was a problem, and it isn't that there was a lack of oxygen, because we could supply that with our solid oxidizers, but you have to have pressure and collision of molecules to feed back the heat, the thermal feedback, to maintain combustion
And
reactions.
have some kind of a containment. So to speak.
Exactly. Initially, and you have to provide localized pressure through containment or very small leaks. You have to generate gas faster than it leaks off. There are several things that I was involved in association with the altitude, and I want to get to them.
Yeah, please do. That's an interesting area.
Well, they involve you.
Oh, really?
That's why I want to get to it. But before
I know what's coming, but go
Before
ahead.
we go into that, one of the programs I got involved in was involved the Atlas Intercontinental Missile Reentry Program. The Air Force wanted to determine what was the best nose cone configuration for the Atlas, and they selected a rocket motor, happened to be an Army rocket motor, the Nike Ajax booster, and they were going to drop missiles from B-52 aircraft at their highest altitude, and then fire the rockets with the Atlas, simulated Atlas nose cones on the front end down to the earth and measure the performance of the nose cones. But the rocket that they selected could not work at that altitude. The igniters could not work. They couldn't stand the pressure differential. They couldn't operate, and we solved that problem for them. We redesigned the igniters, and we were able to make them work properly, and they conducted their program, and I got a commendation for contributing to the Atlas reentry program, which was very important at that time.
That was important, yes.
It was a very highly classified program at the time. They not only shrouded the warheads, but they had gadgets that they hooked onto them to disguise their shape, so that I don't know if it was enemy they were trying to hide it from or competition, but they were hiding the shape. I also presented a technical paper on high altitude ignition in 1957, and the Navy people searched me out. They were involved in the Vanguard program, and they asked a lot of questions, and I answered their questions, but my real allegiance was to Dr. Lundquist and the von Braun team, because they wanted to launch a satellite, and the government had selected the Navy to launch a Vanguard, which, as we all know, the Vanguard wasn't able to perform, and the von Braun team came into play and solved that problem. But I met Dr. Lundquist somewhere in the 1956 to 57 time period, 50 years ago. 50 years ago, or 51, that's when we first met. His office was on the same floor of the building that I worked in. He worked in the Technical Feasibility Studies office with Professor Oberth and other advanced thinkers, and he may have worked for Dr. Stuhlinger.
First it was Dolph Thiel, Dr. Dolph Thiel, and then Dr. Stuhlinger.
Good.
Dolph took another job and left, and Stuhlinger replaced him.
Chuck and I hit it off because he is the type of guy you want to help and support. He was and still is knowledgeable and friendly and willing to share interesting information on military and scientific politics. And so he got me interested in what he was doing, and he seemed to be interested in tracking devices like flares, igniters, photo flash bombs, and small rockets. And we developed mutual interest and collaborated on those things. Charles helped to make arrangements for high-altitude tests in the ABMA facility. It was ABMA at that time, before NASA. And I furnished some of the items, test items, and together we ran high-altitude tests. We ran our own test program of various items, including flares, which we found very quickly didn't burn very well at high altitude and didn't give off much light. The aircraft rockets we tested worked very well with special igniters at the altitude. But it was another wonderful learning experience, for me at least. And as a reward for my help, although Chuck probably didn't intend it as a reward at the time, he invited me to attend a high-level classified meeting chaired by Dr. von Braun and attended by his high-level team and representatives of JPL. The meeting was in connection with preparations for launch of a satellite, and I learned in that meeting the importance of inert weight in an upper stage. I hadn't been exposed to that before, and I believe it was Dr. Stuhlinger talking about the weight of various components in the upper stage, and he got involved in a discussion about the importance of paint, or the additional weight contributed by paint, and that was a topic that took some time to decide on whether to take the penalty involved in painting the upper stage. At times, Dr. von Braun asked his managers individually what they would do to improve the reliability of their product or the success of their mission if he gave them $1 million additional. And if they came up with suggestions for some improvements, he later asked them to accomplish those improvements without the $1 million, which he said he didn't have. I thought that was an interesting approach.
Surely is.
Finally, late in the meeting, as a result of Charles passing my name in, Dr. von Braun introduced me to the group and told the JPL folks that I was an Army employee and I would serve as a consultant on high-altitude ignition of the upper stages of the satellite. However, they did a very good job of design and testing, and I didn't have to contribute or help any. And in January of 1958, the Explorer satellite was put into orbit, and Chuck was a direct participant of that operation, and I congratulate him again.
Thank you. It was fun.
About that time, in May of that year, I left Army employment and went to work for Thiokol at the Huntsville Division to start a new career with them.
See, Thiokol at that time probably had contracts with both Army and NASA, didn't they?
They did. And I was going to mention that Thiokol originally was just a small chemical company. They were making polysulfide chemicals, and they were just struggling along. And Dr. Charles Bartley at JPL decided that he wanted to use their polysulfide polymer, which is a synthetic rubber, as a binder for his solid fuel propellant. And that led to Thiokol becoming ultimately the largest producer of solid propellant rockets in the world.
So you saw the beginning of all that.
Well, yes, I saw part of it.
Okay.
I saw part of it, a big part of it. My horizon was expanded at Thiokol, although I was still involved in rocket ignition. But they were dealing with larger and larger rockets and a large variety, and they had a big customer base, so it was a broader horizon. And I got a tour of the igniter area, which encompassed a laboratory, which I thought was great. It involved a big manufacturing building and an office in a building called the Barn. And that's where I was, in the Barn. That's where I started. In the manufacturing area, I was surprised to see that they had 17 people working full-time making what they called Jellyroll Igniters. And those were igniters where cotton cloth was being coated with a wet mixture of a pyrotechnic, dried, and then rolled, and initiators were inserted, and those were igniters for aircraft rockets, for Falcon aircraft rockets, and some other rockets too. But I told my bosses that the operation was too labor-intensive and too hazardous, and that I asked them to switch to the use of pelleted igniters in perforated tubes or baskets. And within a year or so, we did that, and we eliminated this hazardous, expensive operation. Now, and they were already involved in using what's called Pyrogen Igniters that were originated, and a name was coined here in Huntsville at Thiokol, and is now practiced worldwide. It's one of the biggest advances of that
Describe
technology.
how one works, if you can.
Well, a pyrogen is really a small rocket used to ignite a larger rocket. It's a simple concept, but between the pyrogens and the pellet igniters that I'm speaking of, the concepts offer the ability to make calculations. You can apply mathematical rules to them because it's a fixed geometry, a predictable geometry. You can measure the properties of the materials, measure their burning rates, and all the other ballistic properties, and therefore apply the same rules that you apply to rockets and rocket propellants. And you can now calculate things, whereas before we were just mixing things and making powders and making what seemed like dust explosions, and I consider that we were firecracker jockeys. And well, that led to my contributions in those areas, and I contributed to improving the pyrogens, although the basic work and most of the advancements were by Joe Pelham and Dick King.
See, are pyrogens used with liquid rockets now, too?
I don't know.
Okay.
I don't know.
Some kind of a little rock that
Well,
ignites the...
Yeah, they may call them a torch or something, but
Yeah.
it's the same concept,
principle.
I agree, yes, in principle. One of the first things that I worked on at Thiokol were rocket motors called Spin and Vernier, and they were being supplied to ABMA at that time for the Jupiter. And I'm not sure exactly what they were used for, but I assume that the spin motors were to spin the upper stage or warhead for stability, and the Vernier motor was for additional thrust for a Vernier adjustment. In
little
thrust.
adjustments.
A little
to the
more.
orbit, yeah.
They were both high altitude applications, and they both used electromechanical safe arm devices. Now, I haven't mentioned safe arm devices, but safe arm devices are another, as rocket motors got bigger, we had to have additional protection of everybody, the launch people, and to make sure there wasn't a mistake made, a wiring mistake, or somebody pushed a button at the wrong time. So the safe arm devices provided either a mechanical block or a divert action, so that if the initiating devices were actuated prematurely, the train, the pyrotechnic train, would not propagate. It would be cut off by diversion or just by blocking. And those motors had that.
Those were very sensitive, precision devices.
Exactly. And I also meant to say that the Vernier rocket motor had another feature. It had command termination, which was kind of new, because initially the solid propellant rockets weren't controllable. You ignited and it burned to completion. You couldn't put it out. But the Vernier motor for ABMA, it had command cutoff, which was accomplished by blowing the nozzle off explosively. You blow the nozzle off, it decompresses, and it terminates, depending on the kind of propellant and geometry, and that worked very well too. Another big program that I was assigned to was the Minuteman. At that time, Thiokol had a contract to study and develop, or to study at least, all three stages of the Minuteman. And it was a very, very big program. And it was divided up between three divisions of Thiokol at that time. The first stage was assigned to Wasatch in Utah, second stage for Huntsville, and third stage for the Elkton Division in Maryland. And I was assigned to coordinate between all three of those divisions as far as ignition.
That's a tough job.
It was a tough job, and we divided up the work. But Huntsville, I took the responsibility in Huntsville for the pyrogen propellant, which I decided that all the stages would be ignited by pyrogens. We would provide the propellant, a common propellant, for all three, and we took responsibility for the safe arm device. And there were other things that the ignition train, we would provide the design for that. But the safe arm device is what took real special accomplishment or contribution, let's say. We were in competition with two very competent companies, Aerojet and Hercules Powder, and they were ahead of us. They were several years ahead of us in that area and running behind. And I studied all the designs that I could find that were available and who did what, and wrote specifications for what I thought we needed. And we sent out proposals to various potential suppliers. And we didn't like the proposals that came back. They just seemed too shallow. Then we decided to contact warhead fuse people. And the warhead fuse people, one of them seemed interesting, and Joe Pelham and I went to see them. It was the Bulova Watch Company in New York, Bulova Laboratories.
Really?
And we interviewed them, and they didn't know anything about safe arm devices for rockets. But they understood fuses, they understood electromechanical design, and they understood watches. And between that combination, their proposal was the best. And so we awarded them a contract later, and I was the contact person and provided the oversight, visited them many, many times, and argued many things through.
That's an interesting role they had. I didn't know they had that role.
Yes, they did. And to make a long story short, our design won the competition, and the Air Force awarded Thiokol responsibility for safe arm devices for all stages of Minuteman. And those devices were so advanced and so good that they were a pattern for the industry for many years, and still are at this late date, almost 45 to 50 years later, and they're still being used. In fact, I did consulting for the Army Ballistic Missile Agency, have many times, and I went to Ogden, Utah, to the Hill Air Force Base, and there I saw Minuteman derivative stages being assembled for research vehicles and target vehicles. And lo and behold, I was so proud they were still using my safe arm devices, the same ones, and I was involved in reviewing the pedigree, the paperwork, and those were the same devices that we built in the 1950s. They're still used, they're still workable, and that's because of so many advanced features that we incorporated.
Well, that's a very interesting observation.
Now, I don't know whether the shuttle uses those or not. I haven't kept up, but there are other safe arms now, but they're close patterns to what we developed at that time.
Go ahead.
Another area, I may be getting too long.
No, not at all.
Another area that I was involved in is the Pershing. In the 1960s, the Pershing missile system was being developed for the Army by Martin Orlando, and at that time I was engaged in developing another type of safe initiation device called exploding bridge wire. Exploding bridge wire devices were a type where the initiator was immune to accidental initiation by heating of the filament, which is the way ordinary primers and squibs and initiators are set off, by electrical heating of an element. The exploding bridge wire type, they have a filament of platinum or gold or noble metal of some type, but it's surrounded by a insensitive pyrotechnic or explosive. Sometimes it's PETN, pentaerythritol tetranitrate, is sometimes used, but it requires, for actuation, a high energy discharge in a short time, capacitor discharge. And the ionization and plasma developed is sufficient to actuate the explosive and set off the device. Well, I was working with those things when the Martin Company selected that concept for the Pershing, but they had another supplier, and their supplier was not able to meet requirements at one point, and they had to drop the supplier, and I was able to fill the gap and provide exploding bridge wire initiators for ignition of both stages, and for the thrust reversal ports that required explosive sectors to allow the reverser ports to open and reverse thrust on the second stage. We later upgraded those exploding bridge wire devices by incorporating gaps, spark gaps, which prevented low voltages from even reaching the element, the filament. And when we incorporated the gaps, we supplied those items to NASA Marshall by the hundreds. And I believe they flew on Saturn, but I don't know that to be a fact.
Probably did.
I think that's what they were for. But they were so safe you could plug them into an electrical outlet and nothing would happen. You had to have very high voltages on the order of 3,000 volts from a capacitor. And again, that was a big advance, and those items are still in use in the industry. Of course, all along the line, there were many publications and papers that I was involved in and that I issued. But Diacol was very proud of the fact that they published their own handbook of rocket engineering in 1964, and I wrote the chapter on ignition and ordnance devices, and it's still in use today. I go to places and they pull it out, say they're still using the...
Do you have an extra copy?
No, I don't.
I don't know whether we have one in the archives here or not. It'd be nice to have one.
I'll have to think about that. Much later, Dr. Len Cavaney, who had worked at Diacol at one time, worked with Dr. Summerfield at Princeton, he wrote a survey article a couple of years ago about 30 years of progress in the solid propellant field. His article is called Solid Rocket Enabling Technologies and Milestones in the United States. The article is a requested article. He and 3 other authors are involved. But in the article, Cavaney singled me out as being one of the technology leaders during that period for my contributions in the rocket engineering field, exploding bridge wire work,
it's a
and
great honor.
other things. And that's in the Journal of Propulsion and Power, November, December 2003. So I'm real proud of that. You know, real magazine. One area that's closer to home is the 156-inch booster motor that Diacol static tested in Georgia. Diacol built a space booster facility in Georgia called the Georgia Division, and they built a 156-inch diameter motor, a forerunner of the space shuttle boosters, and it was static tested in February of 1965, and happened to develop a thrust of 3 million pounds, which was really advanced at that time. An unusual feature that, from my standpoint, was that it had aft-end ignition. And aft-end ignition for a motor of that type, it was the motor was in a silo in the ground, nozzle sticking up, and the igniter was suspended above the nozzle or in the exit cone and on a track, mounted on a track with, it was retained by an explosive bolt. And when the igniter fired and ignited the motor, the explosive bolt ruptured and released this igniter, the Pyrogen, very large motor, bigger than this table, and it flew up the track and out of the way of the motor, and then the motor exhausted. And that is another concept that was developed and originated right here in Huntsville at the Diacol facility.
That's very interesting.
The advantage of that type, it's a little awkward for static tests, but for flight tests, it would be the igniter would be below the motor, and it would be out of the way and eliminate the weight of the igniter and the space that it would normally occupy. That would be the advantage of it.
Sure. Now, that was, you had quite a career in it.
Well, there were a lot of things that were involved. I finally got pretty much, or part of the way out of the igniter business when I was promoted in 1968 to be the chief of the rocket engineering section, which was still at Thiokol. And it was a very responsible position that I held for 17 years after that. And it was a very big change, because where previously I was responsible for my own little area, concentrated work in a specialized area. Now, and I had a small part of the puzzle to furnish, now I was being paid to cover a broad area and develop the teamwork and get contributions from the talented people that were assigned to me. And it was a relatively large group, about 30 or 35 people, and they did very well, and we were successful on all the assignments that we were given. But again, it was their teamwork that I was responsible for, and not my individual contribution anymore. We covered a lot of rocket motors historically. To mention a few, if you don't mind, they included Hellfire, Patriot, the Delta strap-ons, Castor 1, Castor 2, Castor 4, Pershing, Nike Zeus, Spartan, Maverick, Standard Missile, Falcon, and Minuteman. That's a host of rocket devices, rocket motors. Someplace along the line there, NASA Lewis selected a group of 4 people to serve on a committee to prepare a design handbook on solid rocket igniters. Don Barrett of Rocketdyne was the chairman. I was assigned to the committee, and there were representations from Aerojet and Bermite Powder. We contributed and reviewed this NASA handbook, which is NASA SP 8051, and it is still being used as the guide all over the country and all over the world. In fact, it's on the internet, and perhaps to our detriment, countries that are not friendly to us, people in unfriendly countries, are using that guide, which tells them how to go about various things involving rocket igniters. Of the many programs that I was involved in rocket engineering, the ones that stand out to me the most are our strap-on vehicles, where we pioneered in strapping large booster motors onto core vehicles like the shuttle, the forerunners of the shuttle, for example. We started out with, our work was initially with McDonnell Douglas on their Thor core vehicle. Thor was kind of a bad word at one time because it was an Air Force vehicle in competition with the Jupiter. But the Thor vehicle, we had 3 Castor 1 strap-ons there, and the core vehicle kept getting larger, the engines kept getting bigger, and the solid propellant motors got bigger, and there were more of them. So we started with 3 strap-ons that contained 9,000 pounds of propellant each. We went up to the Castor 4s, and we went from 3 motors to 6 motors to 9 motors. We went up to 24,000 pounds of propellant each as strap-ons for the Delta vehicles, which are still flying today. And they launch satellites, and it's a great accomplishment for this country. The satellites that were launched and are being launched were for global positioning satellites. There were spy satellites, telephone and television satellites, and in general we were able to provide satellite launches for countries that didn't have television, they didn't have telephones, and once they got satellites, they had all this new communication, and we were very proud of that contribution.
Rightfully so, rightfully so.
Am I speaking too long?
No, go ahead. No, you haven't gone as long as a lot of people have. Keep going. This is great. There's lots of
A couple
very
of other
good historical information in all this.
A couple of other areas that I'm proud of is our technology transfer support to other countries. So one of our technology programs was with Japan, technology transfer. We taught the Japanese how to make caster motors so that their space agency could launch their own international satellites or contribute to international satellites. Late in the program, I was sent to their space center on Tanegashima Island off the coast of Japan, and I was able to witness a test of one of the motors that they manufactured, and it was very interesting and informative because their workmanship was excellent, as we've seen in other areas. Another technology program was with Sweden, and there it involved the rocket-assisted projectile, a completely different type device, a 155 millimeter projectile that was launched from a very big gun, and the challenge was the fact that the projectile was spinning at a very high rate, like 10,000 revolutions per minute, I'm sorry, about 10,000 to 12,000 RPM. And in addition, the setback forces were just tremendous. When you see these big guns fired, you see how they jump. Well, all those forces are directed into whatever hardware is involved, and we were trying to make a rocket work under those conditions for the Bofors company in Sweden. I was there for 6 weeks to start that program, and it was a big challenge, and it involved all the analytical tools that we could get our hands on. And it included, which at that time was cutting-edge technology, because we used X-ray, motion X-ray, movable X-ray, what's it called? Flash X-ray.
Flash X-ray.
Flash X-ray. And we had a rocket motor on a spin stand, one of these rocket-assisted projectiles. It was spinning at 10,000 RPM, and we had a flash X-ray camera next to it that would take pictures of it while the rocket was burning, and we could see what was happening inside. It was terrific technology, and we couldn't have gotten as much information from 100 tests as we got from one by using the flash X-rays. So I thought that was
another very interesting technology. Used elsewhere too, of course.
Yes. From the standpoint of new technology, I was awarded 10 U.S. patents that are all assigned to the government and deal with some aspects of ordnance or rocketry. Later on in my career, I was promoted out of rocket engineering into the quality department. I became the manager of quality, which involved all the quality functions that are normally pursued. And within a year or a year and a half after that, I was promoted again to Director of Quality, which was a top management position at Thiokol. And those areas required a lot of management and involved a lot of people, but the fun of engineering accomplishment was gone. They were very difficult. They were salary-wise, they were rewarding, but the fun was gone. And so in early 1989, I retired. I took early retirement and left Thiokol. I thought I was retiring, but I didn't stay retired very long. Within a year, I was doing consulting work for the Army through Stone Engineering and the Army Propulsion Lab, the same place where I started, the same building, and also for Army Ballistic Missile Agency. A couple of those projects, I thought I'd mention a couple of those.
Please do, that's interesting.
That I thought were good accomplishments. One was that my development of a concept for, and I'm back to ignition again, for simultaneous ignition of multiple motors, clustered motors in this case. We had an application that involved 4 rocket motors clustered together, and the requirement was that they be ignited simultaneously. And I was able to come up with a system using some advanced explosive tools to ignite all 4 rocket motors, and they were about 6-inch diameter and 6 feet long each. Ignite all 4 of them in less than 2 milliseconds, 0.002 of a second, which is very, very fast simultaneity. That was, I covered that in a technical paper. That was one of the things done in there, and later on, in the same laboratory, I got involved in something else. Another interesting project was the development of a process to make finely divided metallic powder by exploding a wire.
Oh.
And in this case, the wire was very heavy, a big wire, several inches long and 1/8 of an inch in diameter, almost a cable.
Aluminum?
Aluminum, yes, in an inert atmosphere, in argon, in a pressurized inert atmosphere. And in order to get enough electrical energy to explode that wire, we used the simulated lightning facility at Redstone Arsenal.
Oh, really?
And we discharged a lightning bolt into a chamber containing argon, our aluminum sample, and we converted an aluminum rod to dust, less than 1 micron diameter dust.
That's how the aluminum dust is made then.
It's an ingredient.
Yeah.
And other metals can be made that way too, but I thought that was really
That is
great.
interesting. I
It was
hadn't
almost
heard about that.
almost like magic. In the ballistic missile area, the interceptor field, I covered a broad area, but the biggest effort of my involvement involved the development of another type of exploding device, exploding foil initiator this time, EFI instead of EBW. In concept, they're the same, but the explosive material is different. The explosive material, in this case, is something that is approved for use in line. The other types, you still have to have a safe arm device, because if you use PETN, for example, it's not safe enough. But if you use another safer explosive, one called hexanitrostilbene, HNS explosive is safe enough to use in line without a safe arm device. But
That's a saving.
yes, it is. And the device, instead of having a filament, it has foil, but the foil is almost invisible. It's so small and so thin, electrodeposited. And the explosion is now, the firing unit, instead of having cables connecting a firing unit to an initiator, the cables are eliminated and the explosive device is in the box itself, is next to the box or sticking out of the power supply, so that there's no losses of energy, no inductant losses, and the initiator receives the energy in a shorter time than ever before, in a fraction of a microsecond. And this device, again, is safe and fires very fast, but the problem that I was involved in is the firing unit, the destruct firing unit, could not meet requirements, and I was able to help determine, or primarily determine, what was causing the problem, why it couldn't meet the qualification requirements. And when they incorporated my recommendations, they were able to qualify it, and it became workable. It was used, and it's being used in the destruct system of a major interceptor missile. And that kind of covers my accomplishments and involvement in the missile field.
Well, you had a very interesting and varied career, very admirable career. Are there any final thoughts you'd like to leave for the young folks that are now entering the field and starting to use and redo some of the things that the old-timers did?
Well, I'm glad you mentioned the young folks, because I mentioned that I'm still doing consulting work, and it's with very young people, but they're very talented, and I'm so impressed with them and their educations and capabilities. And I don't know what message to pass on to them.
Well, you're doing it, though, by consulting with them.
I think they should learn from history so they don't have to repeat some of the mistakes that we made. And I wish them well.
That, of course, is one of the reasons why we're doing these interviews and building the archives, is to let the young people learn from history and make the information available for them.
And I really appreciate the opportunity to meet with you and tell my story
Well,
after 50 years.
thank you very much. It's been lots of fun.
Charles, thanks.